Good day, my dear students. We will now begin with the second session of the lesson from physics, which is motion. I have, as what our usual practice is, listed down the subtopics we are going to study in this session. We will start with a quick revisit to the concept of scalar and vector quantities with examples. We will move on to study what is uniform motion with examples. What is non-uniform motion, again with examples. We will try to understand the basic concept, which is speed, and we will also understand what is average speed. We will now begin today's session with a quick visit to the concept of scalar and vector quantities. We started with this in the previous session, where we learned that scalar quantities are quantities in physics which have only magnitude, right? Magnitude literally for us to understand means size, right? But vector quantities are quantities which have magnitude along with direction, okay? Now look at the picture here. You can see a hiker, a person who's hiking. When I say that the hiker is walking at 3 miles per hour, I am talking about his speed, which is scalar quantity. Am I mentioning the direction here? No. So this has become a scalar quantity. But on the other hand, if I tell you that the hiker is walking 3 miles per hour south, then this becomes a vector quantity because I am defining the direction in which the movement is happening. We move on to the next slide. Here we have a list of the quantities in physics. Now please remember, I have mentioned the basic quantities that we will be using very often. Scalar quantities, it has mass. The examples are mass, length, the distance, speed, power, energy and work. Now these are quantities which I will describe using a particular amount. So these are scalar, but come to the next half of the column where we talk about the vector quantities. When I will be talking about displacement or velocity, acceleration, force, weight, friction or momentum, all of these concepts you will learn as we move ahead. You will find that I will always mention the direction in which this particular movement of force is happening. So all these are examples of vector quantities. We will now go ahead to the second subtopic, which is uniform motion. Splitting the term, we find that we are talking about a movement which is uniform or same. Now what is same in this? Let's have a look at the example that's displayed. I have a vehicle which is moving, right? It started from the origin. Remember origin or reference point? So it started from say 0 meters and it traveled a distance of 4 meters in a time of 2 seconds. So how much time does it take to go from 0 to 4? It takes 2 seconds. Okay. Now, the second part of the journey, the car again starts from 4 meters and it reaches 8 meters. So what is the difference? What is the distance it has traveled? It has again traveled a distance of 4 meters. And how much time did it take to cover it? It again took the same 2 seconds. And likewise, if you see from 8 to 12 meters, that's again 4 meter distance in a time of 2 seconds. And from 12 to 16, which is 4 meters, again in 2 seconds. So what is the observation we have done? We found that the vehicle is covering equal distances in equal intervals of time. So for every 2 seconds, the car traveled a distance of 4 meters and this speed was uniform. So this is what uniform motion is. Whenever a body is covering equal distances in equal intervals of time, the body is said to be in a state of uniform motion. Here equal distances was 4 meters and the time was 2 seconds. Now, moving on, what we usually do in physics is we try to represent graphically whenever two quantities are involved, right? What were the two quantities involved in the picture that was flashed before? One was the distance that was being covered by the vehicle, and the other was how much time was it taking, right? Now, this is the graph drawn for another example. It's not for the example from the previous slide, but let's try to understand. Now, as we know, we've learned in maths, what is along the horizontal is the x-axis, and what is along the vertical is y, right? I have put time in minutes on the x-axis, and as the time passes, what changes? The distance covered is changing. So, I have put distance on the y-axis. Let's understand now. When it was 1 minute, right? How much distance was covered by the vehicle in meters? 10 meters. When the time became 2 minutes, how much distance was covered? Go up, the vehicle had covered 20 meters. Same way, when it became 3 minutes, the vehicle had covered 30 meters distance. Now, in 1 minute, it had covered 10 meters, 2 minutes, 20 meters, right? So from 1, and let me write down 3 minutes also. 3 minutes, it had covered 30 meters. Now, what is the time gap? 1 to 2 is 1 minute, am I right? 2 to 3 is again 1 minute difference. And what was the difference in the distance that it covered? I will do 20 minus 10, which is 10 meters. And here, between the second minute and third minute, what was the distance difference? 30 minus 20, which is again 10. So what are we understanding? We are understanding with equal time intervals, the distance covered is also equal. So this is the graph which represents uniform motion. And the most important point is, in uniform motion, the slope of the graph, you call this line as the slope. This slope or gradient is always a straight line, right? So whenever, this is called a distance time graph. In physics, it's also written as dt graph, distance time graph. And whenever you see a straight line or slope, it means that this graph indicates uniform motion, which means equal distances are being covered in equal intervals of time, right? Now, let me mention at this point itself that this slope that you see here, this represents the speed of motion, right? So, the speed is uniform. The vehicle is covering equal distances in equal intervals of time, which means it's traveling at uniform speed, right? Moving ahead, we will now talk about non-uniform motion. Now, non-uniform motion is the bang opposite of what we discussed in uniform motion. Look at the example again. I have a vehicle traveling. The distance is mentioned here and the time taken to cover that particular distance is written, right? So, the vehicle starts from 0 and reaches a distance of 5 meters. And what is the time that it takes? It takes 1 second to reach from 0 to 5 meters. The next 1 second, the vehicle has travelled from 5 to 15 meters. Now, how much distance has it travelled? It has travelled 15 minus 5, that is 10 meters. Okay? So, in the first 1 second, how much did the vehicle travel? It travelled 5 minus 0, 5 meters. But in the second 1 second, it travelled 10 meters. Now look at it in the third part. It moved from 15 to 30 meters. So what is the distance that it has covered? It has covered 15 meters. Now you will tell me what factor or what quantity has remained constant here and which quantity has kept on changing. Exactly. The time gap, the time that I am considering has remained constant. I have considered its position at the end of every 1 second. But what has kept on changing? the distance that the vehicle actually covered. So when any object covers unequal distances in equal intervals of time, it is said to be in non-uniform motion. So what is saying here? The time duration. What changes? The distance covered by the object, right? This is a very common experience. All of us travel regularly in four-wheelers and two-wheelers, and whenever there is less traffic on the road, what does your parent do? They increase the speed of the vehicle, right? And when there is lot of traffic, they slow it down. So what is the type of movement there? It is non-uniform motion, right? You are covering unequal distances, maybe in equal intervals of time. We will now move on to the next slide and see what we have to learn. Slide, we have come to the graphical representation of non-uniform motion. A quick throwback to how the graph looked in uniform motion. My graph looked something like this. What did I have on the x-axis? I had time. And what did I have on the y-axis? I had distance. And how was my slope of the graph? It was a straight line. Now this was uniform motion. But back opposite, when I am talking about the graph representing non-uniform motion, what do I see? I see that it is a zigzag representation. Why is it zigzag and why is the slope not straight? Because the body is covering unequal distances in equal intervals of time. If you see here, at 1 minute, it has probably reached somewhere around 9 meters approximately. At 2 minutes, where has it reached? It has reached about, say, roughly 18 or 17 meters, right? And 3 minutes, about 30. Okay, so 0 to 1 minute has been 9 meters travel. 1 to 2 minute, the next 1 minute it has traveled how much? 18 minus 9, which is also 9. Okay, but look at the third 1 minute. From 2 to 3 minutes, it managed to go from 18 to 30. So what is the distance that it has covered? It has covered 30 minus 18, which is 12 meters. So is the distance the same every 1 minute? It is not. That is why this is the graph with a zigzag slope that represents non-uniform motion. Now students, we find that we are still left with two subtopics that was actually planned for the session. What we will do is, we will take up these topics first in the beginning of the third session. So what did we do till now in today's session? We started off with a quick recap of scalar and vector quantities with examples. We tried to understand what is uniform motion and what is non-uniform motion. We also looked at what we call as the graphical representation of both the types of motion, uniform and non-uniform. On the x-axis we had time, on the y-axis we have the distance. Uniform motion, the graph is a straight line, the slope, and in non-uniform motion, for all you know, it could be any shape because the object is covering unequal distances in equal intervals of time.